Hey guys, good morning. I needed to give you just a few more notes here before you can do the activity using the PDF that I have posted from our textbook. So if you give me just maybe 5 more minutes worth of some note taking to frame up, then we'll transition over into using the PDF that I've posted and talking about some other neurotransmitters. So, picking back up in your notes, consider kind of where we left off, right? We have talked about how a nerve firing in action potential really is the result of sodium and potassium sort of moving back and forth in a coordinated effort across the membrane of the axon. And so that process is what you need to kind of keep in mind as we talk about this next concept, which is called saltatory conduction. So, saltatory conduction is the action potential sequence that we talked about last time you were in class that happens in neurons that have a myelin sheath. So, myelinated neurons do this process called saltatory conduction. And really, the myelin is essentially an opportunity to speed up the process. So, myelin, remember, is created from, depending on if we're central nervous system or peripheral nervous system, myelin is created from some support cells, either the oligodendrocytes or the Schwann cells. And those cells are primarily composed of fat. And fat provides an opportunity for the electrical signal down the axon to sort of skip the fatty pieces. And so you can see here in the arrows, the electrical signal that is generated at the beginning of the axon can sort of jump this first piece of myelin and touch back down right here on the axon. And then it can jump again, and then it can jump again, and it can jump and jump, landing on these spots called nodes. But basically, what this allows is for that electrical signal, that action potential, to sort of hop its way down the axon instead of having to walk its way down the axon. So it speeds up that action potential movement from front of the nerve cell to the back of the nerve cell. The reason that the signal can do this in part is because of the myelin, but also in part because of a strategy. And the strategy is to cluster all of those pumps that we saw back in class, the sodium pump, the potassium pump that were voltage gated, as well as the sodium potassium pump, cluster all of those protein pumps in the membrane at the nodes. So that means we only have to exchange the sodium and potassium back and forth at one small spot. And so this bullet here that you wrote down, the strategy is to cluster all of those protein pumps at the nodes so that you only have to do the exchange, which was detailed in process C of your notes, at these small spots. Ultimately, the result is that the nerve can conduct an action potential much faster than if it had to exchange ions all the way down the full length of the axon. So saltatory conduction is what's going on in myelinated neurons that ultimately leads to that neuron being able to conduct an action potential really quickly. Okay, so let's talk for just a second about the difference between a couple of signals. So this next section in your notes is called EPSPs versus IPSPs. So these are two types of signals that are received on the dendrites based on the kind of neurotransmitter that's binding. So the E in EPSP stands for excitatory, and the I in IPSP stands for inhibitory, which essentially means that some neurotransmitters excite the neuron and other neurotransmitters inhibit that excitatory process. Okay. So for EPSPs, here's what that acronym stands for: excitatory postsynaptic potential message. So that is an EPSP signal, comes from a neurotransmitter that is going to excite the neuron, which essentially means that it's going to let some sodium start to creep in and start the process of generating an action potential. So this will encourage action potentials to fire, helping to push the voltage of the membrane towards -55 so that that all or none principle takes over. All those sodium gates open, sodium rushes in, and the action potential moves down the neuron. So ultimately, EPSPs, the kinds of neurotransmitters that are excitatory, they open sodium channels and really perpetuate everything that we talked about in class. IPSPs are inhibitory signals. So it stands for inhibitory postsynaptic potential. These are neurotransmitters that work against the sodium channels opening. And so these are, if excitatory messengers are helping to open sodium channels, these are helping to keep those sodium channels closed, which decreases the chance of an action potential firing. Now, the interesting thing is that one neuron is actually receiving all kinds of signals from neighboring neurons. So they're receiving both excitatories and inhibitories at the same time. And there's a little bit of math sort of that has to happen. So the neuron essentially has to figure out, do I have enough excitatories that we can open enough sodium channels that allow the neuron to fire or not? And that decision is weighed at the place on the neuron called the axon hillock. So we labeled that when we drew a neuron earlier this week. It falls right at the beginning of the actual axon. So basically, all of the excitatories are kind of balanced and measured against the inhibitories, and ultimately the nerve decides, did we reach -55 millivolts? Were there enough excitatories to fire an action potential? If yes, all of those sodium gates open and sodium floods in. If not, then the action potential will not move forward. And so this is a quick little model here of that process. So everything that's in blue are the excitatory signals being released. Everything in red are the inhibitory signals being released. And you can see we started at baseline, -70 millivolts, and some excitatories propelled us up. But then some inhibitories dropped us down. And then some excitatories propelled us up, and inhibitories dropped down ultimately until we reach a critical value, and then an action potential can fire. In that process, summation is happening at this spot right here on the neuron called the axon hillock. Okay, so this is where your next activity sort of kicks into gear. And that is kind of understanding some of these neurotransmitters, which ones are excitatory and which ones are inhibitory. So first, let's take a look at them. There are tons of neurotransmitters. I selected a few that are pretty common. Now, for the inhibitories, the ones that actually work against sodium channels opening, we have something called GABA. We have ACH, which we have seen before. Now, ACH in the muscular system is actually down here in the excitatory world, but ACH outside of the muscular system functions as an inhibitory neurotransmitter. Something called serotonin, dopamine, those are inhibitory, sort of relaxing, suppressing neurotransmitters. Excitatories are glutamate and ACH within the muscular system. And so here are a couple of those inhibitory neurotransmitters, things that you maybe have heard of before. Serotonin is our happy or feel-good neurotransmitter. Dopamine is sort of a calming, anti-anxiety neurotransmitter. GABA perpetuates relaxation. Serotonin, again, there's our little happy neurotransmitter. And then glutamate being released is an excitatory. So now you know kind of what category these neurotransmitters fall under. It's time to investigate them a little bit more. So from this point, you are done with the notes part, and you need to transition over to the chart, the paper that I gave you in class that has a chart on it. And you will see these neurotransmitters listed on the chart. You're going to use the PDF that I've scanned from the textbook that's linked on the calendar to fill in the rest of this chart. So you can use this slide in your notes to kind of indicate on your chart which are excitatory and which are inhibitory, but other sections are going to come from the PDF posted from the textbook. So fill in that chart. The very last column of the chart, you'll notice it says leave it blank. That's for an activity that we're going to do tomorrow. So once you have done the first 3 sections of the chart, I believe 2 or 3 sections of the chart, then you can leave that last section blank, and we'll pick it up again tomorrow. Okay, you are done with the video.